Okay. Wait. We're missing a screen. Today we're going to. Oh yeah, right. There's a midterm tomorrow night. There's a programming assignment also coming out probably right after the midterm, maybe even before the midterm. Let's see. Today's plan is to talk about binary search trees and operations on binary search trees. And as a warm-up, we are going to, it's a quiz. The warm-up is a quiz. So you have to decide whether the tree on the left is a binary search tree, and you have to decide whether the tree on the right is a binary search tree using the definitions that we had last time for what binary search trees are. And I will give you approximately 15 seconds. Oh yeah, let's. Okay, done? Tree on the left, binary search tree? Yes. Tree on the right, binary search tree? No. Okay, I know why it's not a binary search tree. It's not a binary tree. It's got like 3 nodes hanging off of one of those nodes. Okay, now is it a binary search tree? Yeah. No, why not? What's another flaw in this tree? 15. What's wrong with 15? It's bigger than 10. Ooh, it's bigger than 11. All right. You got me. It's bigger than 11. So this is a problem. 15 can't be in the left subtree of 11 because it's larger than 11. Are there any other problems if we remove that? Yeah. That is a problem. Yeah. Okay, suppose we remove 21, and suppose we remove 15. Now is it a binary search tree? Excellent. I think it is a binary search tree too. That was a great warm-up. You ready to yeah.
Is it like a trinary search tree? So on and so forth.
Oh yes. There are M-ary search trees. In fact, we'll talk about one version of the M-ary search tree, which is a self-balancing M-ary search tree. It's called a B tree. There's B trees, B plus trees, B star trees. There's all different flavors of B tree. We'll talk about B trees though. We've been around for a while. Yeah. You mean I haven't done that yet? Man. This is just terrible. Okay, I'll do it. But before I do it, we have to get to a point where you have to think about something, and then I'll do it while you're thinking, okay? Is that okay? It'll be like the next page. All right. How could that happen? How could that happen? Because I remember doing it. Okay, never mind. Let's talk about this first, and then I'll go and see what's going on. This function is called pfind. You remember one of the operations that a binary search tree is supposed to be, one of the purposes for a binary search tree is to support dictionary operations, like look up an item given a key and return its definition. And the operation find is the operation that's supposed to be used to do that. This is called pfind. Why do you think that this function is called pfind? I mean, it's supposed to be finding stuff, but it's called pfind because P stands for private. Why do you think that I'm making this thing private? You think about that for a minute and a half, and I'm going to go see if I can fix this problem. If it takes me more than a minute and a half, then you're telling me it's not there. Has it been a minute and a half yet? See, let's just take a look and see if it's in here. It's not? Could that possibly be? Oh, I know what it is. Okay, never mind. Hold on 1 second. This, by the way, is a YAML file for controlling the website. Isn't it great? Except that you have to remember to put stuff into it in order for it to work. And then you just have to use git. Let's use this message. Oops. All right, this should be up in approximately 3 minutes. Okay, why did I call this thing private find? Yes? Yes. Why did I know the private class inside of tree? You're absolutely right. I mean, there's a reason that I did it was because I don't want the external world to see this function find. I don't want them to be using that function find in their dictionary because I want to be able to swap out the implementation details of how I'm implementing a dictionary, and this is giving away lots of implementation details. For example, it's returning a pointer. It's even returning a reference to a pointer from this find operation, which means that somebody can go in there and start messing around with my tree structure, which is so they know, first of all, that it's a tree, plus they can mess around with the internals of my tree, which is disastrous. They could ruin everything. Really. They could tear it all apart. So I don't want to give them that kind of access. So this is something, it's private, so nobody can mess around with it. What did I write down? Don't give out access to the private implementation. We just want to provide the functionality without revealing what's inside or how it's implemented. Yep.
Also, generally speaking, if the function uses something that is defined privately, then that function should most likely be a private function.
For sure. Yeah, this thing is like taking in a node pointer. In fact, that's what these functions are doing because I want to make it clear that some of them are recursive and they use that parameter to be the recursive parameter. So you would pass in the head typically. And so this would be a helper function to some sort of function that would access the private root variable of the structure. So it's even private to the private, it's like doubly private. Anyway, very private, yes.
Also, if this function didn't interact with any privately defined data or other construct, so then in that case we would be able to make this public.
If you wanted to, yeah. Okay, so, but I guess there are these logistical reasons why we have to make it private, and part of the reason why those logistical reasons exist is because when we set up the structure, we made the things that we didn't want to be touched by the outside world private. And so logistically, we are stuck in a corner. But the reason we made those things private is because we don't want people mucking around with our internal implementation of this particular abstract data type. That's why we did it. Okay, so there's some weird stuff going on here. Let's look at what's going on. So when I perform a find operation, why in the world do I need to pass in a reference and return a reference to a pointer? I don't. But I will use this function in the next function, and you'll see why I'm passing reference parameters around. Also, why is the key being passed by reference? Yeah. It could be an object, it could be huge, and you don't want that thing to be copied into your function every single time. So anyway, that's why this is to save a copy. Save, let's call it copying. You don't have to copy. Let's just pass by reference. Okay, so this is recursive code for doing a find operation, and presumably it looks reasonable. It looks in the left subtree if the key is smaller than the roots key. It looks in the right subtree if the key is larger than the roots key. And then otherwise it's lucky. And it returns the root if it's lucky. Okay? You could actually, oh well, let's talk about the runtime. What's the runtime of this code? Log in. I think I'm going to have to, don't write that down, because I'm going to have to be stern with you about this. Didn't we talk about this last time? Is there any guarantee that this tree is nice and fat and bushy? No, there's nothing in the definition of a binary search tree that says the tree has to be balanced. The tree could in fact be essentially a just string of left children, left node, left node, left node, all the way down to the bottom, which means the runtime would not be log n, it would be n. So the runtime could be theta of n if the tree is really badly shaped, if it's very skinny and long. So skinny and long is bad. Bushy and wide is good. We don't have that guarantee for just general binary search trees. In fact, the running time, we could even be more precise about it and say it's something like theta of the depth of the key, which of course is theta of n. And it's only theta of depth of the key if the key exists in the tree. And it's really not theta depth of the key because the depth of the root is 0. It's more like theta depth of the key plus 1. But anyway, it's morally speaking something like the depth of the key. Okay. Why is this code recursive? Why didn't I write it iteratively? Could you write this code iteratively? Probably, right? I mean, it's just, you got to do the same stuff. You have to compare the key to the root, at the root with the key that you're looking for, and you update your pointer to be pointing to the left child if it's less than that, and you update the pointer to point to the right child if it's greater than that, and so you get this lovely iterative while loop to do what this recursive thing is doing here, except there's one thing that will be tricky, which is this is a passed value by reference. It's a reference to a pointer, and you're supposed to return a reference to a pointer. And this turns out to be a little bit messy to do if you want to do it iteratively. But anyway, we could have done this iteratively, didn't have to be recursively, and you, I think, appreciate now the benefits of using iteration over the recursion is that we don't have to do a bunch of call stacks, but the benefits of recursion over iteration is that the code is sometimes more pleasant and readable. Sometimes. This one, it's probably just as easy to read the other one too. Yep.
On an interview, if you could solve a problem doing iteration or recursion, which one would you recommend?
If you're on an interview and you could solve a problem using iteration or recursion, which would be more impressive? I think that depends on who the interviewer is. If it's like, I don't know, somebody that just hates recursion because they had real problems with that, then you're in trouble if you use recursion. I mean, the thing to do what you think is natural. Do what you think is right. I mean, that's... Or you could tell them you could do both. I can do it recursively or iteratively. What do you think? And they'll say, well, what do you think? You're being interviewed. And then you'll say, well, I think... and then say what you think. Okay, any other questions about find? Because the next thing we're doing is insert. Yes?
Just to double check, in this case, what does n represent? Is n representing the number of nodes in the tree?
Correct.
Oh.
N is the number of nodes in the tree. Yep. Because the depth of the root is 0. It's a technicality that I would never, ever hurt you for missing that technicality. But it will be something that other people will be bothered by. Okay, insert. This is, again, a private insert function. We're inserting a new value into the dictionary, into our binary search tree implementation of the dictionary. And so along comes not only a key, but also the data that's associated with the key. Like, for example, we have a new cat that we want to insert into the tree. Let's insert, what did I insert? Oh, yeah, we're going to insert the 8th most popular cat called May, I think. Let's insert that. But before we insert it, why am I passing in a reference to the root pointer when I'm inserting into a binary search tree? Why would I ever want to do that? Look, think about how binary search trees work. When I insert something into the binary search tree, how does it work? Here's the new thing. I compare it to the root. It tells me you're smaller or larger than the root. You can either go to the left subtree or you can go to the right subtree. Wherever you belong, go that way. So what I would do is I'd say, here comes 8 and May. Compare 8 to 10. 8 is smaller than 10. Go this way. Then compare 8 to 5. 8 is larger than 5. Go this way. Compare 8 to 9. 8 is smaller than 9. Go this way. 8 to 7. 8 is larger than 7. Go this way. So it's not in the tree, of course. But that's where it's going to go. It's going to go right here. No, it's not. 8 is 8. Is that where it's going to go? Something like that. 8 is smaller than 9. Okay. That's where it's going to go. Okay. All right, sorry. Got my 8s and 9s mixed up there for a second. The root doesn't change. I put the thing down at the bottom. Why do I need to pass the root as a parameter that needs a reference? Yeah.
It's being defined recursively, so eventually we'll call it.
Oh, okay. This is true for this particular implementation, but I mean, generally speaking, why would I make that parameter mutable? Why would I make it a reference parameter? Why would I want to change it in the caller's scope? Yeah.
If the root was knowing to insert a new node.
Yeah. The only time that I'm going to change that parameter is when the root is actually null. So this is really there if the root, that's the word root, if the root is null, it will change. After insert. But that's really it. So now the real thing that's going on is what you mentioned, is that we're using this thing recursively. We're calling this recursively. And it's kind of a funny thing that it does. It calls find to find where to put the new item. But the new item is not in the tree. So find will fail. Okay. So what does find do when it fails? Well, it fails, it returns, it fails right here. It falls off the end of the tree because it runs into a null pointer, and it says, I give up, and it returns this null pointer. But it returns R. So let's see what that, R is a reference parameter. So let's see what happens. So here I'm going to do this again. So why did I do this? It's because I'm lazy and I don't want to write another version of find. So I'm using pfind to do insertion. It's going to do the descent into the tree. And so what it does is it pfinds from the root, and it follows that pointer to go this way, compares the key against 5, it follows this pointer to go this way. It compares 9 against 8, and this time it realizes that it's actually smaller than 9, and it follows this pointer to go to the 7, and then it compares 8 against 7, and it finds out that 8 is bigger than 7, and it tries to follow this pointer, and what happens is that the recursion bottoms out, and it returns that pointer because it's passing that parameter by reference. It's returning exactly that reference. So this pfind, what did I write? I wrote, it returns, if you're not inserting something that's already in the tree, it returns null. So this right here it returns null, but it returns a particular null. It returns a reference to this null. Which means that if we change that null to something else, it will change this pointer within our structure and therefore add the new node to the tree. And that's exactly what we do. We pull that target, this is the target, this particular pointer, and change it to be a pointer to the new node that we're creating. So it's slightly slick. The reason I'm doing it is not because it's slick. The reason I'm doing this is that I want you to understand that in some data structures, like trees, changing the data structure involves manipulating one pointer. It can be done by using this type of a technique of using a reference, passing and returning references to pointers within the structure. Everybody good with this? This is a little weird. Let me just warn you, this is a little weird. We're going to get to remove. And remove is majorly weird. So if you are feeling slightly uncomfortable about this particular pointer manipulation, please let me know. Like, what in the world is going on? You can just ask that and I will try to explain again. Yeah.
I'm just curious, so if target was defined to just be a pointer, not a ref, not without the reference symbol, so how would that change the function? How would that change the function?
What do you think?
So would it make a copy of the document? I will be sending that copy to the user.
Yeah, if I had declared target to be a node star, the value of target would be null. And you would not be able to, you could change it to be whatever you'd like, but after you changed it, it would be gone.
Or like the tree would be modified.
The tree wouldn't be modified. Just target's value would be changed. And then it would be lost. And you would get this error message which says, from Valgrind saying, you've got a memory leak. So yeah, this is actually a good way to understand this code. If I change this declaration from being a reference to a pointer to being just a pointer, this code would not work. Okay, any other questions about this? Yeah.
What is the reason that key is plus the?
Oh, that's the same reason that we passed them into the find operation by reference. This is just to save us from copying. Save the copying cost, because those things could be large. And presumably you'd want to someplace to find the fact that you're constant, but I didn't put that in there because if you declare them as being constant, then the people that are passing this in know that your data structure isn't going to change the definitions or the keys. Okay. So you already know the answer to this question. What happens when I insert keys into a binary search tree in order? What binary search tree do I create? I insert first 1 with Momo. I'm only going to draw the keys. I hope. And then 2 comes along, and where does it go? And then 3 comes along, and where does it go? And then it creates a chain always going to the left. No, the right. Today is one of those days. That is of length as long as it might be. So if you insert things into a binary search tree in sorted order, it has terrible, terrible performance. If you insert n things into this tree, how long does it take? If this is, instead of being 7, this was something called n, how long would it take you to insert n things into a binary tree if you inserted them in order? Think about this for, let's just say, maybe 30 seconds, because if you get this, this is like important to get. So 30 seconds. The total time to insert all of those items into the binary search tree. N of those items. I'm going to write some choices. Good? Let's vote. How many people think theta of n, the total amount of work done to fill up the tree? Okay, how many people think n log n for total amount of work done to fill up the tree? When you're inserting them in the order 1, 2, 3, 4 up to n. Okay, how many people think theta of n squared to fill up the tree when you're inserting them in order? Great. How many people think theta of n cubed to fill up the tree? Okay. The answer is theta of n squared. Every time I insert, I start at the root, and I walk down until I find a leaf, and I insert the new item. So I start with a tree of height or size 0, and then after I insert 1, I take 1 time unit more. And another one, I take 1 more. So I'm getting like 1 plus 2 plus 3 plus 4 plus 5 up to n. And this is something that you should know at this point is theta of n squared. Okay, great. How much time does it take to do it if I insert them in the reverse order? 7, 6, 5, down to 1. When 7 is equal to n. You can just tell me. N squared. Theta of n squared. It's the same thing. It's really the same thing. It's just going to the right instead of going to the left instead of going to the right. Okay. What about this last one? What's the height of the tree? What is the tree that's produced by this insertion order? You tell me. Let's just go. Here we go. 4. I know where that goes. It goes at the root. Now what? 2 goes left. Okay, great. Now 6 goes to the right. Well, that's interesting. Now 1 comes along. 1. 3. I bet you it's right of 2. Now 5. Bigger than 4. Smaller than 6. And now 7. Bigger than 4. Bigger than 6. 7. What order have I listed these nodes in? I couldn't possibly have forgotten. No, what order? What's the order in which the nodes have been listed? What's it called? There's a name for this. Nope. What is this? The one that says 4 is the first one, 2 is the next one, then 6, then 1, then 3, then 5, then 7. This is called 4, and then 2, and then 6, and then 1, and then 3, and then 5, and then 7. Level traversal. It's level order. So this is a level traversal. Level traversal. You can't read that. Traversal. Level order traversal of complete, not even just complete, but perfect binary tree. Binary search tree. So if I do it in this nice level order, what's the running time of my tree if I did it on a tree with n things? So what if I kept going until I got to n? So it's going to be now a complete tree, because n may not be 1 less than a power of 2, or something weird. But what would be the running time? Is it going to be n squared? Maybe it'll be order n. Should we vote again? We're a democracy. Let's vote. Majority rules. How many people think order n? Great. How many people think order n log n? Okay. How many people think order n squared? Theta of n squared. theta of n cubed. This one is, for this level order thing, it's n log n. But as you know, there's a height limit on a complete binary search tree with n nodes in it. That height limit is log n. And we never take longer than log n to insert any of the elements into the tree, and therefore inserting all of them takes n log n time, big O of n log n time. The question is whether it's really theta of n log n. So it has to be larger than some constant times n log n. But how many nodes in this tree are at the bottom? In general, how many nodes in a binary tree are kind of at the bottom if you have a complete binary tree?
2 to the height.
Yeah, 2 to the height. And in comparison to the total number of nodes in the tree, how many are leaves? About half. About half of all nodes in these nice, bushy, perfect, complete trees, about half of the nodes are leaves. Those are the ones that had to go all the way down to the bottom. And going all the way down to the bottom took about log n time for each of them. So we have something that's taken at least n over 2 times log n time. Same sort of thing that happened when we looked at log of n factorial. Half of that sum is about log of n.
When we're given something like it prints out like a bunch of numbers in like the order you're traversing, if you're given post order, what can you infer about like pre-order and in-order?
Well, what can you infer about them? Sometimes you can infer a lot, and sometimes you can't. It really depends on, I mean, if you give me, for example, in order, like these are all in order trees. I mean, an in order traversal of this tree is, well, let's do an in order traversal. What's the in order traversal of this tree down at the bottom in purple? What's the in order traversal of that? What would it produce? Sorted order. That's one of the reasons why it's called in order traversal, is because it's in order when you do it on a binary search tree. That's really not why it's called in order. But anyway, it's a way to think of it. If I do in order traversal on this tree, I visit the left subtree first, then I visit the root, then I visit the right subtree recursively. So when I visit the left subtree, the first thing that's going to be printed out in order traversal is the smallest value in that tree. And so the numbers that I'm going to get out of an in-order traversal of that tree are 1 through n. Now, if you did a post-order traversal of this thing, you would get another jumble of numbers in some particular order, but and they would be constrained, but the change that I could make to this tree, I can change it's a binary search tree. I can change its structure. I can make it not be perfectly balanced. I could make it be a chain that goes all the way down to the left. And I would still get the same in-order traversal, but my post-order traversal would be different. My post-order traversal would be different for this tree than it would be for the long, like the tree that we produced in the first instance. But the in-order traversals of all three of these are the same. They're always in sorted order. You'd always see 1 through 7. A post-order for that tree up there, different thing. A post-order is the same. It's a different for each of these. It's a great question. Yep.
Also, for this example, binary tree, we have 7 nodes. So then, like, you said that the time that it takes to insert one node into this tree is log n. I was just wondering whether you could, like, briefly explain, like, why that's the case.
Sure. You want it to be log n minus 1?
I think we should actually thought it might be like 2 to the I, because like initially we add 1 node, and then we add 2 nodes, and then we add 4 nodes. So as we go down level, each time we're doubling the number of nodes that we're adding. So that will be the sum from like 1 plus 2 plus 4 all the way to 2 to the end.
Okay. This is a good question about how you have to understand what the cost is here. So when I'm asking about the insertion cost, then the insertion cost is really the number of edges that you're traversing in this tree to put in the new node. So the new node, like for example, we're going to put in, the next node we would put in is, well, we would like it to go over here, so let's call it -1. So we're going to go this way, and there's going to be 2 steps before we get to -1. So for each node that I insert, it's not anything to do with the number of nodes in the tree. It really only has to do with the depth of where it's going to end up. So it's going to end up at depth 3 in this case. And in a tree that has n nodes that's perfectly balanced, that depth is going to increase at a very slow rate. It's going to increase, as you said, by 1 only when you double the number of nodes in the tree. So when you understand that function, if I have something that's only increasing by 1 whenever I double, it's like asking how many times do I have to divide n by 2 in order to get down to 1? It's log n. So the height of the tree, or the depth of the tree, is increasing by just a little bit, just log n. Very slowly growing function of n. Yep.
So, if you repeat again, like how you know it's big omega and log n?
It's exactly the same argument that we had for looking at log of n factorial. We have a bunch of things that are going to be just so quick, you don't even have to think about them. Like the elements in the tree that are at the top, we're not even going to count. Don't even need to. But there's going to be a large number of them, in fact, over half of them, which are going to be right at the bottom.
Yeah.
And at the bottom means their height is something like log n, or their depth is something like log n. So I'm getting half of the nodes with log n depth, so I'm getting n over 2 things, and they've each cost me log n to put into the tree, so I get n over 2 times log n.
For just the bottom half.
For just the bottom half. I don't even have to worry about counting the other stuff.
And then you're just assuming like the top half is like very quick. So.
Well, I'm not assuming that, not at all. I'm just saying that I don't have to worry about it. I'm just saying that the function is bigger than that. If you're asking about big O, or you're asking about big omega? Big omega. I'm just trying to prove that it's bigger than something. So I can just say, well, I don't care how much it took to put in the root, how much time it took to put in the children of the root. I don't care about all of those people that are way up at the top of the tree. I'm just going to tell you how much it cost for these guys, and that's big enough.
So it's a little big O.
Every single node only took time less than the height of the tree to get into the root, to get into the tree.
Oh, yeah.
That's it. Okay. It's good to do this because there's a midterm coming up. And so it's good to review this thing. Okay, what about the average depth? Suppose, here we had this situation where the worst case, it takes order n squared time to do this. If I put them in sorted order, or I put them in reverse sorted order. And then if I put them in perfect order, like the perfect thing, the way you would really want the numbers to come in is level order. Right? That's filling up the tree as best as it possibly could. What do you think the average depth is when I go into a binary search tree? So suppose that instead of inserting the elements in level order or in worst case order, I randomly rearranged them and inserted them into an empty BST. So that's option number 2. Option number 2 would say I'm randomly ordering the elements. And the amazing thing is that if you follow option number 2, I randomly order the elements and insert them in random order into my binary search tree. The amazing thing is that the average depth is log n. Theta of log n. Some constant times log n, like 2 times log n. It's not really 2, it's something a little bit smaller than 2, in fact. But in any case, it's amazing. You can randomly order them and you get basically the best that you could hope for performance. Okay, but now here comes the weird part. The weird part is that if I looked at averaging over all structures, So there's only 1, 2, 3, 4, 5 binary search trees of size 3. If I averaged over 5 trees, my average, and not 5, but n, my average would not be log n, it would be square root of n. So if I average over structures, each structure equally likely, I get an average depth of square root of n. If I average over insertion orders, there are n factorial insertion orders. Each insertion order creates a structure. I get an average depth of log n. Used to be, that's weird, isn't that strange? How could that possibly be true? Somebody is lying. Let's try an experiment. So let's try inserting in random orders, and let's see what happens. So suppose I choose 1, 2, 3. Which tree will I get when I choose 1, 2, 3? You can tell me it's tree A, or tree B, or tree C, or tree D. Or 1, 2, 3 goes where? 1, 2, 3 would create which tree? If I inserted the items 1, 2, 3, which tree would I create? A. 1, 2, 3. If I insert 3, 2, 1, which tree do I create? E. 3, 2, 1. Excellent. So that's 2 of the 6 possibilities. What about 2, 1, 3? 2 goes in first, then 1, then 3. 2, 1, 3. Okay. How about 3, 1, 2? 3, 1, 2. Everything's smaller than 3, so it all goes into the left child. Okay, what about 1, 3, 2? B, 1, 3, 2. What about 2, 3, 1? The whole. So if I generate a random permutation, I am more likely to generate a tree that's shallow than I am to generate a tree that's not shallow. That's what this picture is showing you. Even for nodes, even for a number of nodes, which is just 3, you can see how this dilemma is resolved. This seemingly it's like, logically, how does this work? You know, but the reason it works is because when I choose a random order, I am not selecting the trees uniformly. I'm biasing the selection to trees that are short, shallow trees. I get more probability on shallow trees than I do on the deep trees. Isn't this cool? It's totally cool. And in fact, what we're going to do is we're going to analyze this average depth log n, but not today. Because we're not even going to do it tomorrow or the next day. We're going to do it sometime in the future. But I have 2 minutes just to tell you one more thing, okay? Everybody okay with this? Okay. The one more thing I'll tell you about is find min. This is a warm-up for the remove function. So this function returns the minimum key in a tree that's rooted at the root. Where would I find this minimum key? What do I do? Here I am at the root. Which way should I go to find the minimum keyed thing? Should I go to the left or the right? Go to the left. Then go to the left again. But what if the left is null? Should I go to the right? No? What do I do if the left is null? Stop and return it. So this is the minimum. If this is the root, this is what find min returns. This is the minimum element in the tree. And oddly enough, this is a building block for doing remove. And we'll talk about remove next time.